And take it away. I think you can introduce yourself, but I'll just say briefly that Lukas is a veteran founder and speaker. He started CrowdFlower, I think, like one of the original crowdsourcing platforms, and that transformed through several incarnations. And he basically hosted Bay Area AI meetup and spoke at it. So it's really great to have Lukas back. And just one thing I'll mention is that he also speak at Scale by the Bay conference, which is in October 28 and 29, also online, but with a lot more immersive tools than here. We'll have, special chat, we'll have Discord and so forth. So we really, encourage everyone to join Scale by the Bay, and information will be sent to the meetup. So with that, Lukas, take it away.
Okay, awesome. So I'm Lukas, and I hope I didn't miss the mark here. I was actually intending these slides for an audience of kind of engineers who didn't necessarily have a deep background in ML. The ironic thing is that, normally who I talk to is ML engineers. So I can kind of tailor this. I feel like I could have used one of my stock presentations, but I made a custom one for you guys, sort of assuming less knowledge. So anyway, it'll be fun. I mean, it's a small group, which is fun. I mean, if people want to jump in and talk and interrupt and stuff, I think that'd be more fun for me as a speaker, just because it's a little bit, it's a funny feeling speaking out into the void of people that you can't see. So if people do want to, interrupt and ask questions and talk about their experiences, that'd be fantastic from my perspective. The things that I wanted to cover in this talk is, like I'm saying here. So basically, first of all, I want to talk about, basically how ML, like what's really working in ML today. And actually, you guys have some interesting, perspectives here. I mean, a lot of you are at companies that I work with and companies I don't work with. I'd love to hear kind of your take on how it works. And then I also wanted to sort of talk about, my perspective on like why ML engineering is kind of different, and why like new tools are needed. I spent most of my career making machine learning tools. And so, I have a strong perspective that new tools are needed, but not everyone shares that perspective. So we can talk about that. And then finally, I wanted to basically show you the products that I've been making recently, less as a sales pitch and more just that's the thing that I know the best is the products that I'm actually working on. So I kind of wanted to walk you through the products that I'm making now and kind of how I think about that, and maybe get some feedback from all of you. Does that sound good?
Yep.
Want to get you talking a little bit. So like Alexei said, my background, I started a company called CrowdFlower. CrowdFlower became renamed itself as Figure 8 and sold to a big Australian company called Appen a few years back. And we basically we're a training data service for machine learning teams. So I'm not going to talk about that today, but I spent probably over a decade working on the kind of training data, human loop active learning problem. And then after that, after Figure 8 sold, I started Weights and Biases, which I think of as a developer first MLOps platform. I'll say, I think we work with some of the folks here. We work with Cisco, and we just actually announced a partnership with NVIDIA yesterday, but NVIDIA's been a customer of ours for quite a long time. And we've had a lot of conversations with the various AI teams. So it's a big company, but I don't know, Achal, have you actually heard of Weights and Biases? Did you come across us at NVIDIA?
So I haven't come across it as a part of my work, but I did watch an interview that you did with Nico. He is my director. So is it? Are you actually working with my org, or or is it something?
We kind of do a bottom-up strategy, so we don't always know, but we've I think at this point we've sold NVIDIA several hundred licenses. So
I see.
I don't know where the teams live, but maybe not your org, because you sort of make a product then for car companies. But I love the interview with Nico.
Yep.
Link in the chat. Cool. So yeah, you know, that's kind of where I'm coming from here. I thought it might be fun to tell you, you know, before I did all this, actually, back in like, you know, 2004, 2005, I worked at Yahoo, which was kind of a big deal, you know, back then. And you know, this was quite a while ago, but you know, I was basically running the ML program to make the search engine work better. And so we were actually switching from kind of essentially like a hand-tuned system with like a little bit of gradient descent on the parameters to like a full-on ML system. And I thought it might be fun to just show. I was thinking about my workflow back then. So back then we built a gradient boosted tree system. So we had basically human labelers label search results as good or bad. And then actually we used an R package called GBM back then. I even, you know, at that time, wasn't obvious that Python was like the language of choice for ML. I think R was pretty, you know, the new research algorithms would get built in R first. And so I actually remember I wrote code to sort of take the trees and generate C code, like literally C code with a ton of go-tos, you know, because it's essentially a random forest. And then, well, it's a gradient boosted trees, I guess, so slightly different. And we would actually check them into the production code that would run live. And I remember the engineering team like asking me like what the hell I was doing because the diffs were so enormous back then. But these models were like small compared to what you'd see nowadays. And by the time I left Yahoo, I had checked in, I think, as much code as every other team combined because the code was being automatically generated. And then, you know, we would basically deploy it into production and then test it on evaluation set, which like is not really best practice in my view, but, you know, it was too hard to test the search algorithm in any other way. It was too expensive to really build a test cluster at the time. Then we do an A/B test, and then we would deploy it into GA. And the whole process took about a month or two, you know, kind of from, you know, original training and seeing that a model was better to deployed into production. And we ran into all kinds of problems with this process. I think like kind of every, you know, ML malfunction that I'll talk about, we hit with this. So anyway, I have worked as an ML engineer, now mostly serve ML engineers. So I kind of wanted to first, like, I guess, ground things. I mean, you all have a perspective in this since most of you are actually working in ML. But I do feel like there's like a lot of hype out there. So kind of wanted to talk about the applications that I'm seeing. I actually think like, you know, I don't know how you all feel, but to me, if I was graduating with a background in ML, this would feel like a really exciting time, I think. Like, I remember when I graduated in 2004, I really felt like, you know, I loved ML, I loved doing ML, but, you know, there weren't very many companies out there. It was sort of like you could rank advertisements or you could rank search results, or you could work for a hedge fund where it was kind of like the career opportunities for actually doing ML. And now there's just a crazy number of options, which are all very cool. I'll say, I think like one thing that people, I think one misconception people have is that there's these like massive breakthroughs. And I think like mostly what I've seen, you know, over the last 2 decades working in ML has been more sort of steady iterative improvement than these sort of like step function changes. Of course, like I think when the application starts to hit a threshold, sometimes you get like a step function change in adoption, but sort of interesting. I just pulled this, there's a lot of graphs like this, but this is like, actually in The Economist, they were trying to, you know, sort of look at speech recognition error rate. And you can see it's, and it is on a log scale, but you can see it's kind of a steady, reasonably steady improvement, but then, you know, suddenly you hit this threshold in speech recognition and, you know, everyone is willing to like use an interface, right? Like, I feel like most people these days, you know, if they don't care too much about privacy, they, you know, they use Alexa or Siri or things like that. So, you know, it sort of feels like a step function change in adoption of speech recognition, but I think from a algorithm performance standpoint, it's a much kind of smoother curve. I'll say I just kind of want to give you a quick tour of the stuff that I see that I think is really cool. One of my favorite examples, I don't know if any of you have seen this before. This is a subdivision of John Deere called Blue River. And this is actually deployed in fields in California. This is a vision application They were actually customers of my last company, Figure 8, and Weights and Biases. So I know this really well. They basically look for weeds in a camera facing down in a tractor, and then they try to spray just the weeds, not with pesticides actually, but with fertilizer. And so the fertilizer burns the weed and kills the weed, but then the fertilizer is useful for growing the plant. So I love this example because this is the thing I really would have loved to work on, coming out of grad school. Because it's like, it really, it uses pesticides. There's sort of less impact on the environment. It's actually like more efficient, right? It saves money. It means you can grow more plants. And it's also like a really cool use case. And it's really only powered by ML, right? Like if you mess up, if you spray the lettuce with your fertilizer and burn it, you're really gonna cause a problem. So it's like a really high value application for the farmer. I'll say like we actually got them to do a really in-depth case study. So I say case study, it sounds sort of like it's going to be like this like kind of businessy high level thing, but actually we were able to convince them to publish a lot of their code that they used and actually their whole tech stack. So if you really want to get deep on how ML is working at John Deere for this application, I put this link in here, wb.me/John Deere, that I would totally recommend checking out. I'll say that their stack is pretty typical of what we see these days, right? It's basically PyTorch on top of Slurm, which they use to manage the workflow, and everything runs on Kubernetes and Docker. This is all in training, and then they're actually using Jenkins as their CI tool, which is typically that's actually kind of not necessarily ML only, but that's what they use to deploy into production, and then kind of Onyx to do the edge deployment. I don't know. Have any of you heard of this use case before? Am I using this too much? Is this news to any of you? Achal, have you heard of this use case before?
Yep. This is not new, but yep.
Not new. Yeah. I guess it's fairly well known at this point. And can you tell? I guess can you say something about the use cases that you're working on?
Yep. So I work in the dataset development team. So basically, we build the so when you're training a machine learning model that goes and sits in the car, you want to know what data that model was trained on. So my team is responsible for giving out data releases where we have some standard set of data that's collected over through different mechanisms, ingested, indexed, and you could have a data requirement that's like I need 3,000 frames of nighttime data in Japan. And my team is responsible for fetching that data, basically driving the cars and packaging it in a way that it can be consumed for training.
Wow, so when you say fetching that data, you mean literally driving it. It's not like looking at a database for that data, it's driving the car.
Yeah, it's a bit of both actually. So we already have data that's ingested and indexed. So if part of that data requirement is met, so we first check do we have the data that meets this requirement, and then if we do, we figure out a way to package it, version it, and send it out to the perception team. If we do not, we figure out, okay, where do we drive to get this data? That's basically what we do.
Wow, that's super cool.
Yep.
Do anybody else want to share the use cases they're working on? I'd love to hear these. I'm trying to remember who said they were an ML engineer. Maybe Geeta, you said you were working on some of this stuff, right?
Actually, I'm not actively working on it. I did in the past. I worked on the system for the US Post Office to sort mail.
Really? Wow, that's so cool. Really? To decide where.
Yeah, this was in the actually in the 1990s, I would say. So it was deployed by the post office to sort mail back then.
Were they using like a learning algorithm to do that in the 90s?
was using neural networks and different, but neural networks were kind of not practical to deploy then. So they were rather small, not very deep ones, just a few layers.
But still neural networks in the 90s for the post office.
Yeah, but we also had a lot of other algorithms, more traditional ML algorithms, and we also did classifier combination kind of approaches. And there was a lot of image processing as well in that application.
Oh, cool.
Yeah.
And anyone else want to share? I mean, Neil, you're a bit vague about your applications. Do you want to tell us about any that you're working on?
Oh, I worked on a bunch of stuff on search and worked on infrastructure at Oracle. We use machine learning for search at Google. You obviously don't want me to go deep into what we did over there. Yeah. So I've worked a lot in machine learning. I mean,
What were you doing at Oracle?
huh?
What about at Oracle? Like, what were the kind of key?
So Oracle, the main thing I did was build a runtime platform for machine learning.
And what were the models doing that you were using the runtime platform for?
Let me increase the volume. What were
the models that you ran on your runtime platform? What were they? What was the purpose?
Oh, it's mainly for SaaS applications, things like resume ranking or which inventory item to order next, that sort of thing. So pretty much every area. I mean, Oracle has a very large SaaS group, about 17,000 people at least. So lots and lots of different use cases. So this was horizontal infrastructure, not vertical stuff.
Cool. Well, these are cool. Thanks. Anybody else want to share?
In search integrity for our company, we are using the human level data and the pipelines to reduce integrity, reduce harms, all sort of problem for Facebook search. We have some cool applications as well, like in AR VR for Oculus Cast. And also there are some interesting other applications other than the voice assistant and all of that, that is to actually automating the process of reviewing PRs.
Really?
Yeah, like things that can really mess up the production, like can create a save or something. So finding those interesting scenarios in automated way with machine learning signals and generating features for that. So there would be some interesting cases I would mention.
Wow, that's really cool. Man, I want to hear your talk on that. That's I did not know that was really working in the real world. I guess I'll just mention a couple more. I think I would say one big area where we see quite a lot of real energy going. So my last company did not do hardly any work with pharma companies, and now at Weights and Biases we see a ton of drug discovery work, both at kind of startups like in Citro and others, and then at like the pharma companies like Genentech and Roche and AbbVie and others, and there was a really exciting announcement I think about a week ago. Google kind of finally open sourcing at least the sort of runtime of their AlphaFold algorithm. So we actually we made a little collab where you can run AlphaFold on your own protein sequences if you want to go to this short link. But I think I guess drug discovery, maybe we don't have any drugs on the market yet that are FDA approved, but my feeling is that this is definitely coming down the road. I'll say just other stuff that we see quite a lot of. There's a lot of interest in robotics and vision. I think the vision working more than the robotics, right? So for example, we see robots going up and down aisles to check prices in the supermarket. I think here, the navigation, like reliable navigation, has kind of turned out to be harder than doing the vision recognition of what items are actually on the shelves. And so you see like standard AI, building stores that you can go into in downtown San Francisco, and basically like it'll automatically watch the stuff that you take off the shelves. It's been kind of interesting to see the vision. I think is feels a lot more kind of usable in the real world than robotics at this point. Other like medical applications, I think medical imaging has been like a huge growth area lately, especially with like, kind of deep learning helping vision algorithms work better. So we see, kind of precision medicine in lots of various forms. I mean, people often talk about cardiology and radiology, but I think, maybe where we see this the most is in identifying cells in microscopy, right? Where you're looking at exactly what the cells are, which are the cancerous cells, kind of what shape do the cancerous cells have. And what that'll do is let you know both sort of like diagnosis of exactly what type of cancer does someone have, and then also prognosis of, how severe is the cancer. So this is definitely, this is getting real world adoption. And then autonomous vehicles. I mean, we have some people, here like Achal that know more about this than I do. But there's obviously in the last couple of years, there's been just an explosion of interest. I mean, not just not just cars, but like delivery robots and drones and many different takes on this kind of semantic segmentation problem. And then I guess I wanted to sort of like pay a nod to like, I think the vast majority of what we see are maybe these less sexy applications like, demand forecasting, credit scoring. We have a little demo here in wandybw.me/xgboost to sort of show kind of a very real world inspired credit scoring situation, but like most of the stuff is kind of less, beautiful for slides. I couldn't even figure out what would be a good image to put for credit scoring, but I think nearly all of fintech is doing some version of this. And then there's the adjacent kind of like fraud detection, which is basically all moved to ML. I sort of imagine that these are pretty similar to the types of stuff that Neil was talking about at Oracle. I'm sure you had some of these applications. So I guess, I want to talk about how like kind of machine learning engineering is sort of different than, kind of like software engineering. And I'll probably be preaching to the choir here, but I will say, when I started Weights and Biases, a lot of the pushback that I got from people, I wanted to start, this is about maybe 4 or 5 years ago, starting a MLOps company making like developer tools for ML engineers. A lot of the pushback that I got was like, hey, do we really need different tools for ML than we do for software engineering? And actually I have a great interview, Achal, I think you'll especially appreciate this with, this is with Anantha, who was at the time the person running the autonomous vehicle program at Lyft. And he was basically like, actually his background is not in ML, but his perspective on ML, he's actually at Facebook now. But his perspective in my interview with him was really like, ML is not so different. People act like it's different, but really it's just a subfield of software engineering. We just hire people in that. We kind of use mostly best software practices to get this deployed in the real world. So if you want to counterpoint to what I'm saying, I definitely recommend going to this little link that I have here at the bottom and checking out what he had to say. I think like there are clearly a bunch of differences though. And I think the first one is that all the software abstractions get broken when you switch to deep learning running on a GPU, right? Like I feel like just that switch from a CPU to a GPU or a TPU, it sort of breaks the whole stack. And I feel like, I remember in like, 2003, 2004, kind of feeling like I encountered my last linker error. But in the last couple of years, I've been running into like a lot of linker errors, right? Because, I'm using CUDA, which is sort of less mature. And like, I think like when you break the very bottom of the stack with the GPU, you end up with like a whole new stack. And so like just actually setting up an environment to do deep learning is like a huge ordeal for a lot of people and requires like a lot of knowledge of hardware and software. And it really matters, right? So I think like, another thing I'll just like note is that, Kudanan is this library, or Kudanan is essentially a library made by NVIDIA. And it really is just like a kind of a compilation layer from like, hey, I want to run a CNN, and then compiles it into CUDA code that then runs on a GPU. And it is amazing how much performance gains you can get from optimizations in that library. So I don't know if any of you are kind of hardware people, but this always feels magical to me that you could get like a 2x speed up from a new version of such a low level library, right? Which I think shows there's just like a lot of room for improvement, across the stack, right? And so, again, this is maybe for, someone who's not deep in ML engineering, right? But I think like, you'll have like, on top of Kudanan, you'll be running Python, then typically be running PyTorch, but, even that is often, too low level of a library. Like typically we'll see somebody running Lightning, or on top of TensorFlow, they're running Keras, right? And that's actually the main interface that we typically see our customers engaging in deep learning. And then finally, now you see this explosion of interest in even higher level libraries, like, I'd sort of consider Hugging Face in this category, where people are basically starting with these frameworks, right? So there's quite a deep stack now, and the stack is totally different from software engineering. Another point that I'll make, and I'm kind of preaching to the choir here, but it's like kind of worth noticing, is like, the ML model looks a lot more like machine code than human generated code, but there's like some other key differences here. The ML models these days are essentially the size of the RAM on your GPU. So these are like, typically like gigabyte size things that you're deploying. We see our customers making, thousands of them. They're not diffing them, right? So like you train the same model on 2 different days in the same training data, it's functionally equivalent. But literally every single character in that file is different, right? Whereas like, if you have like a V2 of your software stack, you might change 10% of your code, would be a lot. And it would be sort of like in specific areas where you could look at a meaningful diff, right? But, the ML code just does not diff well at all. And so I think what happens is, you see that like I'm saying, debugging is really more like observing what's going on in your model and then, making adjustments, right? So Andre Karpathy gave a talk at our user conference a few years ago, and he talked about, amount of lost sleep over data sets or models and algorithms, right? But like, notably here, I think if you're a software developer, you wouldn't be losing sleep over data sets or models and algorithms, right? What you would be doing is looking at, like requirements and stepping through your code and modifying your code to like fit new requirements. I mean, here you really you have this option of sort of like changing your model algorithm, seeing what it does, or changing your data set and seeing what it does. And it's much more like observing what the model does and then making adjustments. So I'll give you an example. Everybody talks about like explainability problems with neural nets, but it's kind of interesting, where explainability has gone, right? So this is one best practice that we see for explaining what an image algorithm does. And it's basically blanking out different parts of the image and seeing what changes, right? So, this is an image of a dog playing an acoustic guitar. And if you run it through, like a ResNet, you basically get sort of 3 labels: electric guitar, which is wrong, acoustic guitar, which is right, and Labrador, which is right, right? And so in this case, I guess electric guitar is the highest probability at 0.32. And so you want to look at why does it think that it's an electric guitar? And it's interesting, right? So like, if you basically blank out ranges of pixels, you can see which pixels are contributing most to the decision that it's an electric guitar. And you sort of see it's the fretboard and it's the person's hand kind of pointed upwards, which makes sense, right? That looks just like an electric guitar, and it needs to kind of learn to also see that the body of the guitar makes it an acoustic guitar. But I think what's interesting about this, right, is it's not stepping through the model at all, right? I think like when a lot of software developers get into deep learning, they really want to look at, okay, like what are the weights at every layer? They want to like walk through what's happening. And I think that was like hard even back in the days of sort of like, 2-layer, multi-layer perceptrons or SVMs. It was not really feasible. I remember back at Yahoo with trees, people always wanted to step through the trees, but it never really led to insights. But I think now it's just completely infeasible to walk through what the model's doing. So instead, what people do is they sort of treat the model like a black box and observe what it does, right? So here we're kind of modifying the input image into the model and seeing what changes. So the explainability, it's a funny notion of explainability. It's really different from software where you're not really explaining what it does from a kind of first principles approach. You're more treating it like a scientist might. And so, what happens is I think like debugging ML is incredibly hard. There's actually, I don't know if any of you have taken the full stack deep learning class. It's a free class online. It's really, really excellent. And lecture 7 is one of my favorite lectures on debugging. And, I think like one of the issues here is that, you can get all these different problems and none of them causes the systems to throw errors at all, right? And this may be an opportunity in ML tooling to kind of, suss out these problems in advance, but basically, bad hyperparameters, bad data set, like, bugs in your implementation, they all look the same, which is just that, there's no error. It's just like your model performs worse, right? And so debugging is a real challenge. Actually, I'll note that they actually, this is a bug that I've had, and this took me a week to resolve, I remember, for me, which is, I don't know if any of you know this, GLOB is not deterministic. So if you run the GLOB function on a big set of files, you'll get a different order each time. Did any of you know that? This is beaten into my head because I ran into this. What happens is basically if you use a GLOB for the features and you use a GLOB for the labels where those are in files, they'll mismatch, right? And so what'll happen is you'll basically get, it'll be like kind of impossible for your model to perform well. So that's like just a maddening bug. But anyway, I recommend going to this link where they have tons and tons of materials on debugging. But again, all these things are really more around making small changes to the way the model trains and observing what happens versus kind of stepping through the model's code. I also, I think like another really interesting thing, and this is like maybe for like management problems, but I'm mostly a manager these days, but like we just really don't know what's hard and what's easy in ML, and we never really have good intuitions at all. And then like, I go back to the movie 2001 Space Odyssey, right, where there's this amazing scene where the astronaut, banters with the computer and also plays it in chess. And apparently they wanted to take out the part where the astronaut beats the computer at chess, which is so interesting, right? Like, because chess actually, computers got better than humans in, I think like 96 with Deep Blue, and better than the average, it was better than the best human in 96, better than like the average human, maybe in the late 80s. But in the 70s when this movie was made, they wanted to actually remove the part with the chess playing, because that seemed just so impossible that a computer could win at that. But then they didn't, consider the fact that like bantering with a human is almost an AI complete challenge. So we should be very, cautious about, our predictions on how ML is going to perform over time and what problems are easy and hard. I kind of came across this running a Kaggle competition, which Kaggle is this site, I don't know if you all know it, where you can basically submit problems and then you can kind of pay a reward for the person that gets the best solution. It's actually kind of amazing if you want to sort of see how hard a problem is, because you'll get a lot of people, like thousands of competent people engaging with your problem with like a prize of say like $20,000. So I put a task in here. There's actually a search relevance task. So, Neil, you'll find this familiar. Basically predicting the relevance of a document to a query. And, the accuracy basically doubled in the first 3 days, right? So, I was like thinking, wow, this is going to be maybe too easy of a task. Maybe we'll get to like 99% accuracy here. And actually over the next like 90 days, it just completely flattened out, right? And so you can imagine as a manager of a project like this that had this kind of character, it'd be incredibly frustrating, right? Because you'd sort of be predicting, great success for your modeling, and then, you completely run into a wall. And this is like, the best teams would run into the same wall, because this is thousands of teams across the world competing. And the line here is their best accuracy. So, there really is like, without like a, change in like the state of the art of relevance, this is kind of the best accuracy that they can eke out of such a system. And, we see the same thing. I mean, the self-driving cars, I hate to pick on it, but I think they're the worst offenders here, where you see like in 2015, this graph of like the miles per disengage that Google published, right? And so you see this kind of exponential looking curve. You could totally imagine extrapolating from this curve, like, wow, self-driving is, going to get solved in the next few years. And of course, there's one guy who keeps doing that, right? So Elon Musk in 2015 says, we're going to have full autonomy in, 2 years from now, which would have been I guess he's predicting 2018, then he changes the prediction in 2017, kind of looking at that curve, and is clearly wrong there. So the forecasting is super hard. I mean, software, you say like, what's the rule of thumb, like for any project, like double it and add one or something. I think, for ML, it's just like, you have no idea. Like if your problem may be solved tomorrow, maybe solved never. And I think we just really don't know how to tell what things are easy and hard. I think there's other thing that's kind of related, which is this, what we call the reproducibility crisis. And Pete Worden had like the initial blog post on this, which I think was really good. I mean, he's sort of like talking about a problem that I think has kind of plagued ML for a long time, which is like, it's actually getting harder and harder to reproduce the work in the state-of-the-art papers. And it's actually more and more important, right? Like most teams these days are actually reading the papers and really trying to get right to the state of the art, which is, I think, different than other fields. There's just a rich, I mean, the academic work is incredibly relevant to teams. You don't necessarily want to take all the complexity of it, but for example, when Google published Transformers, when Google published Attention Is All You Need, that got into language systems, in 6 to 12 months. It was deployed in a lot of the state-of-the-art language systems that you'd run into. So I guess for someone that's not in deep learning, you might wonder why is reproducibility so hard? Because software is pretty deterministic and pretty reproducible. I mean, there's threading issues that are maddening, but other than that, not so bad, right? And so there's just actually lots and lots of places where stochasticity creeps in. I mean, one is just literally the order of operations in your GPU is not necessarily deterministic, right? So you solve everything. You nailed down your random number seed, kind of all the upstream data. These days, reproducibility still might not be possible just because of the scheduling, right? So I think really when people talk about reproducibility, there's many different levels of it. And what I would say is that, there's sort of the more constraints you put around yourself, the more reproducibility you can have, but truly being able to run the same learning algorithm twice and getting out the exact same model, I think at this point is basically impossible. There's this interesting checklist I think put out by McGill, and you can see that it's a pretty detailed checklist, pretty tough. I mean, probably worth doing, but there's quite a lot you need to get right to get reproducibility. And then Andrew Ng put out made this point that basically deep learning is continuously sort of increasing our ability to consume more data and get a better model, which causes us to build bigger and bigger models. And as the models themselves, just even training them, gets on the order of magnitude of days or weeks or more, reproducibility just gets really infeasible. There's a great summary blog post from OpenAI, which talks about kind of the breakthrough algorithms and their resource consumption. And clearly that's just exponentially increasing. And you might say, well, maybe that'll stop, right? Maybe, we'll kind of figure out ways to train more efficiently. And then there's tons and tons of work, just there's lots of work on model explainability, but there's lots of work in model explainability because explainability is hard and getting harder, right? So the fact there's all this work in explainability doesn't mean that explainability is on the verge of getting solved. And then, with resource consumption, it's kind of the same thing where there's a lot of work on improving the resource consumption, kind of getting more with less cycles, because these models are so resource heavy. And actually, I think this blog post is kind of famous. This graph, you might have seen it before, but I think this graph may be more important and got less attention, which is that basically the resources needed to train models to AlexNet level performance have also been decreasing exponentially. So while the overall resources going into the biggest models is increasing exponentially, the efficiency of training is also increasing exponentially, right? It's just kind of increasing exponentially at a lower coefficient. So I think this kind of shows you, and I really recommend going to this blog post. I put a link here. What this says to me is that basically, as things get more efficient, it actually becomes more rational to deploy even more resources at a problem, because you can get even higher levels of performance from your models. So I don't think that the resource consumption problem is going away anytime soon ever. I think actually resource consumption is going to continue to grow at an exponential rate. And then I think, Achal, you were talking about this a little bit, but the dependency graph is getting more complicated for real world use cases, because typically the data set that goes into training a model, some of that data is generally generated by upstream models. And in a way, there's things that you might call model training might not, but like, kind of data pre-processing steps can be critical for model performance and typically happen asynchronously from the model training. So, a lot of our customers just want to know, hey, I deploy this model in production. There's this one piece of data that I got a takedown request from. I want to make absolutely sure that that request, that data that someone wanted to remove is not in my deployed model. Seems like a simple question, actually really hard for even the best companies to answer right now. And then kind of a big effect that's happened is essentially transfer learning. I think transfer learning has been around for a long time. This is like where you basically, you have one place where data is cheap and one place where data is expensive, and you do your training on the thing where data is cheap, and then you fine tune it or you kind of do the last step of training on the more expensive data. And I think the really amazing application of this was the dermatology paper in Nature, where basically these scientists trained a model on ImageNet, which is like pictures of stuff on the internet. And they fine-tuned it on images of cancer and built a state-of-the-art cancer detection system. But this is in imaging, and I would say, transfer learning is like table stakes in vision at this point, but it's also, I think, at this point, table stakes in language processing. And this is like, you'll think of word embeddings. This is like one way to look at that is kind of a transfer learning. So there's BERT, there's GLB, there's GPT-3. In fact, people have talked about prompt engineering, which is kind of a new concept where you don't even, with BERT, you would actually kind of include the BERT embedding into your model. Prompt engineering is kind of something anyone can do. I think it's like a very engineering approach to this, but the idea here is basically you take like GPT-3 and you literally just sort of like give it a couple pairs that you fine tune on, where it's like in English, you say, give it a sentence, and then you give it like a translation of that sentence. And then what GPT-3 will start doing is just replicating that, right? So here someone made, an emoji translator by just like putting in a few examples of emoji. And then GPT-3 did an amazing job of building a emoji translation system. And this, works in some cases, not in others, but I think we're going to see more and more of this, this type of thing. And then, finally, I'll say, I don't want to get like too deep into the ethics in AI in this talk, because it's a big topic. But I think we obviously have seen a lot of cases where people have been worried about models deployed, like they sort of exhibit bias. Often the bias comes from the trained data. It can also come from the embedding these days. So it's hard to imagine what even an unbiased trained data set would mean. But even assuming you had that, bias can creep in from embeddings, and people have been embarrassed in lots of different ways. And I think it's only going to increase, and scrutiny is going to increase. There's a great book, Real World AI, that was written by actually my old head of product, Alyssa, who works at Blue Cross Blue Shield now, but kind of goes through the different cases and gives some suggestions, especially for this is kind of especially good, I think, for people at more managerial level, to like how to kind of organize organizations to avoid this. But there's a lot of case studies around stuff that might happen. So anyway, I wanted to talk about I want to make sure that I get a chance to talk about the stuff that I'm actually like working on right now, and how I'm thinking about that. And I think like the thinking behind my company, Weights and Biases, was something that kind of bothered me for a long time, where like I feel like there's like this developer workflow where you you basically we kind of know how to deploy code into production, right? You never build a system that didn't include version control, that didn't include CI/CD, that didn't include monitoring production. There's like all these companies that actually do these things for you, and open source projects, and just sort of best practices around it. And it felt like we're increasingly deploying ML models into production applications, and the workflows are totally ad hoc, right? Like most of the people that I talk to don't use Git to version their models. And I think the reason is, like I talked about earlier, the models don't diff well, the model files are enormous, the diffs even aren't that interesting. And also there's sort of like, multiple different projects happening at the same time in a sort of like, workflow. And so you actually want to have different version controls and lots of different stuff at the same time. But anyway, where people end up typically is they're putting their models into, S3 buckets or GCP buckets, and that's crazy, right? I mean, like that's really dangerous. I mean, for some applications it's dangerous. For some applications it's dangerous, and that it could cost the business lots of money. But I think there's a clearly room for improvement here. And so these are the kind of developer tools that I've been working on, and I'll kind of walk you through some of this stuff in a second. Also say, you know, this is kind of in contrast to other ML ops things that I think are also really interesting, right? So like, you know, there's also kind of like AutoML stuff where it's sort of like automate the entire process. I think DataRobot is a great company that does this. Google AutoML is a really cool product that works, you know, phenomenally well in a constrained environment. I think the issue with AutoML really is that I think that companies are not precise enough about what they're trying to optimize for. Like in the real world, you're not really optimizing typically for one metric, unless you're like a hedge fund, and then maybe you can optimize just for making money. But even then, there's like risk as a factor, and you know, but for like a typical application, there's actually a lot of factors, you know, kind of at play. And so I think like, you know, AutoML can really be kind of like dangerously over optimizing. And I'd say in the real world, mostly people don't do pure AutoML. And everyone's been saying for the last like 20 years that like, you know, AutoML is a couple of years away. And my perspective is that, you know, we don't see like software getting automated away. And so I kind of don't think we're going to see like ML getting automated away. Of course, we'll get more and more automation, but then I think it'll lead to new problems that you'll still want an ML engineer for a good long time. There's also kind of these pre-built models, and a lot of companies do this, right? Where it's like, you know, hey, I have a credit scoring model for you. Maybe you can fine tune it. I don't see a lot of this, a lot of traction for this. I mean, it's a really good idea. It seems like really useful, but it does seem like every business has like slightly different variations on exactly what they want. I just don't see a lot of pre-built models getting used in, you know, production. If you see differently or think differently, I'd love to know about it. And then finally, there's like this whole genre of company that's like more about this kind of data pipeline and giving you like a place to train your models. And you know, Databricks, SageMaker, Paperspace, all these products that I really respect. I think they're all very good in different ways. And they some of them call themselves ML ops, but it's a much lower level definition of ML ops than I think about that at Weights and Biases. I'll also say, you know, like, you know, I think like people probably get like a lot of entrepreneurs coming here like pitching vaporware. We have something that a lot of people use. I mean, you know, Facebook research uses this quite heavily. You know, in Citro is like a big bio company uses heavily. NVIDIA, you know, like I was mentioning, uses this a lot. And I feel, you know, I feel really proud of this. I mean, like, you know, I'm making software for people to use. And so it feels really good to see teams actually find it useful. And I'll show you what it does in a second, but I kind of wanted to say like things that are like important to me in the product. I mean, the one really key one here, I think, is interoperability, which is actually a really hard thing to do in the ML space because it's changing so fast, right? So, you know, I think if you're trying to make an ML tool, I mean, one challenge that you have is like 2 years ago, probably TensorFlow was the most popular framework, and it's probably switched to PyTorch, you know, in just the last year or two. We see like Lightning getting a lot of momentum. I mean, things are changing super fast. I mean, Hugging Face kind of came out of nowhere to become like standard in like feels like a year. So kind of in this changing world where people have like lots of legacy systems, lots of new stuff, I think you really have to be able to work with everything out there, because most real world teams that have been doing this, you know, for a while, they have a bunch of different systems. I mean, even it's funny at Facebook, you know, you think like they make or they're like famous for making PyTorch. You know, you see a lot of cafe there. You see a lot of experimentation with Lightning and fast AI and lots of different stuff. I mean, boosting algorithms where it makes sense. And I'll say like the kind of way that we wanted to design the product was sort of like, you know, these kind of three principles in mind. Like one is like a really simple integration, just because, you know, everyone's so busy. Like we want people to be able to try it really fast. And then we want to make the ML developer's life like individually really easy. But then, you know, once their life is really good, we wanted to add, you know, collaboration on top of that. So I'll kind of show you, for anyone that's left here, I'll show you a quick demo of how our stuff works. So, you know, typically, you know, we see training code in Python. That's the vast majority of what we see. And so you basically would import our library into your training code would be the typical starting place. So you know, you import a library if you're using Keras or Lightning or PyTorch, we have kind of specific integrations for those libraries. So in Keras, it's a you know, 1DB callback that you'd add to your training function, and each library is kind of a different natural integration. But the important thing is like 2 or 3 lines. And then what happens is, as you're training your models, it's reporting as much as it can about what's happening. So you get these nice graphs of like the accuracy here. So this is an example of training, actually a semantic segmentation algorithm trained on roads. And so you can see the gradients, you can see actually here, so you can see the actual task where there's an image from a car, like a car and a road and a sidewalk. And then the goal here is to label the car and the road and the sidewalk and the bicyclist here. And so you can already kind of see, why this is like a complicated task, right? So like, road accuracy here looks kind of flat. If we look at, car accuracy, maybe that's going up. I mean, human accuracy, you can imagine is like, extremely important. Traffic accuracy may be less important, right? So, here we have a case where the traffic accuracy is going up, the human accuracy may be flat. Hard to know if this is like if this model is really like working for the use case we have in mind or not, even though here the training loss overall is going down as the model trains. We also try to capture as much as we can of the model so you could reproduce it as much as possible. And it's sort of like the more best practices you include, the more reproducibility you get, right? So, we'll save the Git repository and a diff against the latest Git state. I think my strong recommendation for ML practitioners is use Docker everywhere. So if this person was using Docker, we would have, the Docker file saved. So you'd have like, the state of all the libraries and things like that. We also save the hyperparameters and basically as much as we can to make the model reproducible. Then I think like one of the things that we realized in the course of this is that, looking at like an individual run is not as relevant to an ML engineer as looking at like a whole bunch of runs together, right? Because what you're really doing here is an investigation of sort of what data, what hyperparameters, kind of what strategies lead to better models. And so here we make this big table where you can look at, kind of all the different runs or all the different experiments that you have and the input values, the hyperparameters really, and then the output metrics. So you also like, you kind of generate graphs, you can generate these things where you can explore the space, and try to find the regions where maybe your traffic accuracy is higher. You can also, do things like, look at what parameters are important with respect to some metric. Actually, what we do behind the scenes here, this was kind of, I think, a longstanding best practice among researchers, but no one ever really published a paper on it. We basically train a random forest where the input is the hyperparameters and the output is the metric, right? And so then we look at, because random forests have a great, they're really robust, and they also have a great notion of feature importance. We can say like, okay, here the config parameter num valid is probably the highest importance, even though the correlation is smaller. And then using probably an AlexNet encoder has a strong negative correlation in this case. The correlation is a lot higher, but the importance is about the same, which means that it interacts less with other features. And so this is like typically the place where like an ML engineer would live in our product. But the thing we really want them to do, because we really want collaboration here, is to hit this create a report button. And so what you do here, what happens when you hit that create a report button is you can actually save a snapshot of something that you did. And this is almost like a pull request for an ML engineer, where you could say like, okay, it looks like AlexNet has worse performance in this case, right? And now I can save this report. And the nice thing here is that like this investigation that I did, where it's actually a negative result, right? So I probably wouldn't publish this. Probably wouldn't talk about this too much. Easily could get forgotten. But now it's saved forever. So if someone else comes in and they're thinking about AlexNet, they can find this report. They can see that that was kind of the case. They can see my conclusion. But importantly, they can also investigate it, right? So they can say, okay, these were the 224 runs that led to that idea. What was the state of the code at the time? What were the hyperparameters considered? And you can decide if it's like relevant to you or not. I should say, like, one thing that I'm really excited about is that a lot of folks have a lot of our academic users, and make it free for academics is basically they will publish kind of mini results that they have kind of in the tool here. So if you actually go to www.ai/FC, you can see a big curated list of different results that have actually been published on our platform. So you can actually find a lot of kind of like quick little nuggets of like what works and what doesn't on different use cases. So the next thing that someone like typically wants to do in this case is do a kind of automated hyperparameter search. And like, there are a lot of tools out there to do hyperparameter searching, both like companies and open source packages. There's like Optune is a great one. Raytune is a great one. There's a company called SigOpt that got bought by Intel. And, you know, I would say like actually using all of these, they're a little bit different, but the truth is like, they're all really good. They all will actually save you a lot of time and trouble. But what we saw when we interviewed our customers is that actually most of our customers are using none of those tools, right? If they're doing anything that's kind of like a hand-rolled optimization system, we're kind of asking why. And I think that there's like a real barrier to entry. And so what we tried to do is basically wrap these open source libraries and just make them really easy to use, right? So what you can do is you can basically, like, once you have, you know, a set of runs that you did, you can basically just create a sweep. And what this does is actually guesses a set of configuration for you. Because another problem with hyperparameter search is there's quite a lot of hyperparameters, right? Of exactly how do you want the hyperparameter search to work. So we tried to make this safe for you. So we use Bayesian optimization. By default, we use Gaussian processes with small amounts of data. As you get to like bigger sets of data, we switch over to TPE, which is a strategy that kind of scales better. We guess the parameters that you're looking at, and we guess what the distributions are. So again, we try to make, you know, if you really understand hyperparameter search and you want to, like, you know, customize the meta parameters here, you can go nuts. But the thing we really wanted to have happen is just like, I feel like everyone at some point should be switching over to Bayesian optimization, because in almost every task, it'll save you compute and you'll find a better set of hyperparameters. So the cool thing here is, like, you hit initialize sweep. This works on any set of infrastructure, because what you then do is you just run this WB agent command anywhere. It can be inside a Docker container. It can be in a collab. It can be literally like in any kind of infrastructure. And that's just actually going to ask the server, hey, what set of parameters should I run next? So this super simple system, it kind of works anywhere. And we try to make it so easy that like anyone, you know, would want to do this. I guess some other stuff, you know, beyond that, that I can show you is, you know, the kind of next big request that we always get from people is, hey, can you version my data sets and models? And this is actually kind of a complicated problem. We looked at a lot of the stuff out there. We ended up rolling our own system with kind of, again, like an eye towards simplicity. So so we version your data set, but we also keep track of like who uses it, because that's like a big question. So like, so basically, you know, here's like 5 versions of my training data, and actually each one is used by a different run here. So I can go into the run and I can actually see exactly, you know, what the input artifacts were, which is typically a data set, and the output artifacts here, which is results and a model, right? So I'm kind of housekeeping, not just the data set, which needs to be versioned in a smart way, you know, because you're often making incremental changes there. We're also sort of simultaneously versioning the outputs and allowing you to attach like metadata to that. And I'll show you just one more thing, and then I'll be quiet here. But you know, like another huge issue that we saw, and I think Achal was kind of talking about this a little bit, but basically just even finding images in a large data set, or finding like examples of training in a large data set, it can be like a real challenge, right? So we've kind of built a system where you can actually see. So here we're like seeing your data, right? We're seeing you know, the semantic segmentation and then summary statistics, and you can filter it down into ways that are kind of like, you know, useful to you as an ML practitioner. So maybe I want to look at just you know, rows where like a certain fraction of the image was a bus, right? So like, you know, maybe places where at least 1% of the image was a bus, right? And now I'm like seeing all those, and I can say, well, maybe I want some percent to be a bus, and I also want to find images where there's some prediction of like a bicycle in there also, right? And I guess that filters down to that case. I guess wasn't in my data set. Maybe if I make it a little more open-minded. So now there's a prediction of a bus and a bicyclist in here. And these expressions obviously can get really complicated, you know, because a lot of what you're doing as an ML engineer is just sort of exploring your data sets and trying to figure out what was going on. I can also kind of group this. So look at like what the dominant prediction was. So here, you know, are the data sets where my main prediction was a truck, right? And here's one where my main prediction was a pole. I guess void means maybe there's not like an obvious main prediction, but they can also see, okay, for the data sets, across all the data sets where, you know, there's like a lot of truck in them, what was the propensity to predict building and wall and fence, and so on. Again, all this is kind of in support of like a fast understanding of what the training data is, because that's such an important constituent to how well the model is going to work. And I'm over time now, so maybe I'll skip some of the stuff. But I did want to leave anyone who is interested in ML and an engineer, but not an ML engineer yet. I kind of wanted to offer it's something that I really think is great. I think when engineers get enough ML to be dangerous, I think that's actually really valuable to companies, and also can lead to a great career. We see this all the time. So I'm super passionate about engineers kind of retraining in ML, and I think the best resources are one is Fast AI, which is a great resource, great community, and totally free. Another is Kaggle, which is a place where you can actually kind of get practice doing ML. And the CTO of OpenAI actually learns ML, he said, entirely from entering Kaggle competition. So there's no substitute for this kind of hands-on learning. And they now have a lot of new programming around just tutorials on ML, a super friendly community. And finally, say we've been putting out content based on popular demand on kind of getting engineers into ML. And so you can also follow www.me/IntroML. And then, if this is interesting to you or you want to talk about it more, my email is lucas@wmb.com. Are there any questions? I realize I went a little bit long there.
Yep, I have a question, Lucas. So you showed me the data set, searching within the data set. That's super cool, by the way. But my question is, how do you make that a generic thing? So is that specific to image data? How can I use the same thing to train, say, a model that does natural language understanding, or how do you make that a generic thing? Is it?
Yeah, no, totally. It's totally generic. We actually, so we, yeah, so we often use image examples just because they're the most beautiful examples. So they're the most.
Yeah.
But most people don't use that with images. So basically, we have kind of like a type system that so we can kind of know if there's a sensible thing to show you as an image or a graph or a number or whatnot. And then basically the math that I typed in gets compiled down to a GraphQL query to store everything in a graph database underneath the hood, so we can kind of do that fast querying, and it's all kind of lazy, right? So our goal is that you can see your data live, so that you can kind of do that that exploratory use case on a really large data set. I can put in actually, the best place I think to learn more about this, probably just in our docs. I'll just put that in the in there. But yeah, that's I'd say the two use cases we're really considering here. It's input data and then also evaluation data, right? So when you run a lot of models on the same data set or the same set of data sets, being able to see which ones, where are things working, where are they not working.
Yep, that's really cool. Yep, that's it.
Yeah. Question?
Thank you.
Other questions? I think there was a question earlier about the slides. So if Lucas shared the slides, which he graciously said yes, we can just post them under the meetup for all the folks.
Very cool. I'll send it to you afterwards.
Hi, I'm Tosif here. I had a question. There's this, I work for a banking client and I'm located in Pittsburgh, where the client is right now. And one challenge or one project that we work on is trying to see if any sensitive information about a particular customer is like not leaked, it's properly redacted in, for example, in a bankruptcy case, for example, or in a foreclosure process. So I know there are OCR tools to do that, but can I use like machine learning models like CNNs or and neural networks to identify those redacted information in those documents instead of like, manually scraping through those long 20, 30 pages to PDFs.
And redacted sort of means, I'm just picturing this, it means like there's like is it like in the movies where there's like a big black block over the...
Yeah.
Yeah, I mean, I would imagine that's a really easy vision task. So I mean, yeah, I think with a pretty small amount of data, you could train a model to identify like redacted regions. I mean, it almost seems like you could almost do like...
Yeah, but I need to look for specific redacted information, like, for example, account numbers or date of birth or like license plate number, for example.
I see. So it's maybe a kind of a combination of a vision and like a language processing task, possibly.
Yeah.
Yeah, I mean, it's an interesting question. I would say that I mean, this kind of reminds me of kind of structured data processing, which I think is like one of the most common real world tasks that we don't see as good of a set of like kind of open source libraries for like, handling structured text data. I don't know if anyone wants to post in the comments like anything that they're seeing that's useful there. I feel like that's a case where people tend to roll their own systems because there's kind of a dearth of stuff. But I do think you could view it as a vision task where you're sort of like looking for these images, or you could OCR it and then view it as a language task. And I think it's hard to know a priori. It kind of depends on how accurate your OCR system is, like how well that's likely to work. But yeah, you could try both approaches.
Okay.
I have another question relating to the data set visualization stuff that you showed me. So what debugging, what tools for debugging do you offer, and did I miss it? Or is there a way for me, let's say I identify my model is performing poorly because of a bad label. Is there a way for me to identify during using some debugging tool to figure out which label was the root cause and which version of my data set was it present in?
It's a great question. So I would say right now there's not an explicit debugging tool, but I do think there's a couple best practices that we've seen a lot of our customers use our table to find mislabeled results. So we might, what I would recommend actually is basically, if you look at your, first of all, simple thing, if you look at your training data, so your model running on your training data, and you look at where the highest residuals are, the highest error, those are often mislabels. It's a great place to start, right? Is to look at the training data that your model has trouble classifying even after it's trained, right? So just like empirically, that's like a really simple query that you can do with our tool or any tool and find mislabels. And then we actually have a plot that I didn't show you where you can look at across all of your models, the error on your training data and also the variance of the performance in the training data. And so basically things with low variance and high error rate, those are most commonly the mislabel. So the case where your model is just like always getting it wrong, it's either a mislabel or there's something like funny about it, right? So like, you'll often you'll find on like, ImageNet, there's a bunch of like completely black images that get labeled, I think, with tardigrade. So you end up like black, and it's the easy way to find funny stuff is like the low variance, consistently high error things, which is like, and also relabeling those is the most important because those are actually affecting your model the most, right? Because, typically the models are optimizing for loss, which is typically something like the squared error or categorical cross entropy, even worse, right? Where like, the models are emphasizing the really hard to classify examples. So that's definitely the place to start. The other place to look is the, ones where there's high variance and a high error rate tend to be just like difficult ones. So that maybe less consistently like errors or mislabels, but also worth looking at, because those tend to be like the really hard examples. So, once you've trained multiple models, you can kind of get that's the best lens for finding mislabeled examples.
Got it. Thank you.
These are great questions. I really appreciate them. I'm sorry. I wish I had done a more technical talk with this audience. I sorry I misjudged you guys. I'll get more in the weeds and scale by the bay. What? Any other questions?
Going once, going twice. All right. So there is no more questions. Let's all thank Lukas. Really, really great group today, and thanks for all the questions. And I think the topic is right on for this audience, because first of all, we have a large audience on functional TV, which will see the video of this, right? And so that, I think, the core of the community are more into data engineering. I think software engineering is moving to data engineering, eventually becoming kind of encompassing engineering, right? So I think that really hits all the notes. But I would just say, reproducibility, kind of tuning, debugging, right? These are all kind of engineering questions, and I think you really hit it, like all the questions, how you deploy it, right? This kind of a perennial question, and a lot of people, like there is a whole ecosystem of startups around this. So I think it's really helpful to kind of see. Louis just shared a link to Fully Connected on your site for NLP, and I just went. It's really amazing, updating set of news and topics. So that's I think it's really helpful. So thanks again, Lukas, and we are looking forward to seeing you in the community and at Scale by the Bay. So thanks, guys.
Thanks, Lexi. Always great to talk with your group. Have a good one.
Bye.
Thank you.
Thank you.
Thank you.